Welcome students to the 7th lecture of Logic and Distributed Control System. So today we are going to discuss about the programming of PLCs. Mainly we will focus on relay ladder logic. So what is relay ladder logic? A relay ladder logic, that is in short RLL diagram, also referred to as a ladder diagram, is a visual and logical method of displaying the control logic which based on the inputs determine the outputs of the program. The ladder is made up of a series of rungs of logical expressions, means each rung is representing a logical expressions expressed graphically as series and parallel circuits of relay logic elements such as contacts, timers, etc. So each rung may consist several logic with the contacts, timers, and counters and several other elements, and each rung is representing a logical expression. So each rung consists of a set of inputs on the left end of the rung and a single output at the right end of the rung. That is a very basic philosophy when you are developing a relay ladder logic or RLL or ladder diagram, that in left hand side you may have the thousands of inputs which is required to develop the logic, but at the end, means on right hand side, it should ended with a single output. That is the basic philosophy of ladder diagram. So other languages, it is uh, here we have to understand that other than ladder logic, though the ladder logic is very familiar to us, other than ladder logic there are other languages are there by which the PLC programming can be developed. So there are also other languages to program a PLC in than the RLL. What are they? Now most of the significant manufacturers support about 3 to 5 programming languages. Some of these languages such as the RLL have been used for a long time because there are several advantages are there for which the RLL is very much famous among these 3 to 5 other languages of PLC programming. While most manufacturers used similar languages, these were not standardized in terms of syntactic features. So previously what happened, though the 3 to 5 languages are available, which is not standardized internationally. Thus, the programs developed for one would not run in another without considerable modifications, often mostly syntactic. Means suppose the symbols, symbols, addressing scheme, and several things are not standardized. So what can happen? Suppose the language which is running in developed by running in a PLC developed by someone else may not run in the another. So that's why in the last few years there has been effort to standardize the PLC programming languages by the International Electrotechnical Commission, that is IEC. So IEC 1131 is an international standard for PLCs formulated by the International Electrotechnical Commission. As regards PLC programming, it specifies the syntax, semantics and graphic symbol for the PLC programming languages. So what are the other languages? Now, ladder diagram already we know. Other than this, sequential function charts, SFC, function block diagram, FBD, structured text ST and instruction list IL. So these are the programming languages are available for PLC, and by IEC 1131 their syntax, semantics and graphic symbols are standardized. So in short, we are going to know that what are the other programming languages and how the programming is written in that programming language. And in between all these languages we will give special emphasis on ladder diagram. So in this course we are going to learn extensively that how with the ladder diagram we can write the PLC programming. So here the classification has been given, that is PLC programming languages. It is divided in two categories, that is textual language, another is graphical language. In the category of textual language, that is instruction list and structured text, and the graphical languages are the ladder diagram, functional block diagram, and sequential function chart. So in brief, in this lecture we are going to know that what are these languages are. So here one graphically it has been shown that the traditional software architecture of the PLC. So any machine we are going to control by PLC. So the PLC basically read the inputs, and code will be written any of the languages, maybe the ladder logic, functional block diagram, instruction list, structured text. Then what is other one, that is sequential function chart. So so whatever the inputs are read, and then whatever the languages you have written the code, based on that the logic will be executed, and which is going to energize the set of outputs by the PLC. So now about the ladder diagram language is the most commonly used PLC language and is designed to mimic hardware relay logic. That is actually most important factor for which the ladder diagram is popular. Exactly, it is going to mimic the hardware relay logic. So that's why the transformation from the hardware relay logic to the ladder diagram was smooth. Means those are the operator were habituated with the hardware relay logic. For them it was very convenient to understand the ladder diagram, because exactly it is going to mimic the hardware relay logic. So here you see, if one hardware relay control circuit, a typical example is shown, that is suppose push button switch, and the control relay are there. One control relay CR1 is represented normally open, CR2 is normally closed, and with this PB1 and CR1 there is a OR logic with the LS1, that is the limit switch is there, and then this whole logic is ANDed with CR2, and ultimately the output is solenoid valve maybe. So now when you are going to write the equivalent ladder programming, then just the switches or contacts are going to replace by contacts. That is suppose PB1, CR1, CR2, LS1, you see exactly the same it look like, and it is ended with a coil which is representing the solenoid valve. So in this way we can understand that the ladder diagram language is the most commonly used PLC language and is designed to mimic the hardware relay logic. Now we will try to understand the functional block diagram. The functional block diagram programming uses instructions that are programmed as blocks where together to accomplish the certain function. So suppose we are going to execute the AND logic. So two contacts are ANDed, that is A and B. Then the functional block diagram for this logic will be that AND boolean, and two inputs are there, A and B, and the output is shown by this. Then suppose A and B, the two contacts are in parallel, means they are in a OR logic. So then OR boolean, then A and B are the inputs, and here you see A and B are ANDed, but B is a normally closed, means it is a negative logic. So what we can do now, we are using AND boolean A and B, but B is inverted. So in this way the functional block diagram for the equivalent logic will be available as a library function when you are using the programming using functional block diagram. So here a typical example has been given. Suppose sensor 1 and sensor 2 are in a AND logic. to energize a pilot lamp, that is 1. So then you can use the functional block diagram, equivalent functional block diagram, where the input 1 and input 2 is coming from the sensor 1 and sensor 2, and the output is connected with the pilot lamp 1. So according to the sensor logic, if both the sensor having input 0, then according to the output logic, your output also will be 0, and the PL lamp is going to glow only when the sensor 1 and sensor 2 are both in high logic. Okay, so in this way the equivalent functional block diagram is or can be represented, which is represented in the ladder diagram here. Okay, now third language is the sequential function chart. This is also a graphical language. That this programming language is similar to a flowchart of your process. The program is split into steps with multiple operations happening in parallel branches. So that initial step 1, some action has to be performed. Then the step 2, another action has to be performed. Then here the looping is there. So in this way it is going to work. So the sequential function chart programming language is similar to the flow chart of your process. Then other two very important languages are there, that is which is using text to execute or to represent the hardware logic. That is, instruction list programming language consists of a series of instructions that refers to the basic and, or, and not logic gate function. It is something like your microprocessor programming, the machine level language what you have done, something like that. So here you see the same logic which we have performed with the ladder logic, that is same hardware relay control circuit is present. So now how we will write the instruction list? Now start with the PB1, which is ANDed with CR1 with both the start switch and then CR1 is ORed with LS1, and then AND NOT with CR2, and finally the output is the solenoid valve. So in this way the instruction list programming language can be written for a hardware relay control circuit. And the structured text is a high level language primarily used to implement more complex procedure. So here you see so many number of contacts are there, which is representing the different sensor input, and ultimately the solenoid valve is there. This is the ladder diagram which is shown. The equivalently the structured text program we can write if sensor 1 and sensor 2, because these two are ANDed, then solenoid valve is going to be energized. Else if sensor 3 and sensor 4 and not sensor 5, then the solenoid valve also is going to be 1, then end if. So in this way you can write the structured text for a given process. Now in between all these languages you will find that the relay ladder logic, that is all simply the ladder programming, is familiar to or very popular to us. Why? Now for the programs of small PLC system, RLL programming technique has been regarded as the best choice, because a programmer can understand the relation of the contacts and coils intuitively, because it is just going to mimic the hardware relay logic. Additionally, a maintenance engineer can easily monitor the operation of the RLL program on its graphical representation, because most PLC manufacturers provide an animated display that clearly identifies the states of the contacts and coils. Although RLL is still an important language of IEC 11313, as the memory size of today's PLC systems increases, a large sized RLL program brings some significant problems, because RLL is not particularly suitable for well structured programming. It is difficult to structure an RLL program hierarchically, because this is the disadvantage exists for the RLL programming. So the ladder diagram language is a symbolic set of instruction used to create the controller program. So it basically consists of contacts and coils. So as I said that at left hand side you should have the inputs, and it in a single round multiple branches may be there to execute the control logic, but it should end it with a single coil as an output. So each rung must have a single output. So representation of contacts and coils are the basic symbols of the logic ladder diagram instruction set. So now we want to know that here basically you will find that two categories of contacts we are going to use, that is NO and NC, normally open and normally closed. Now how these normally open and normally closed contacts which is used in the ladder diagram programming are keeping similarity with the electromagnetic relays. If we come to know that how the electromagnetic relays are working, then it will be very fruitful to understand that how the NO and NC contacts are going to work, and this will be helpful to develop the programming when you are doing with the ladder logic. So electromagnetic relays have been used for a number of years to switch a high power circuit from a low power system, because the relays will be low powered but it is going to actuate the high power circuit like motors. So these relays suffers from spark damage. So microprocessor technology now provides a more reliable and maintenance free alternative to the relay. So nowadays we are using not the electromagnetic relay for the development of programming or ladder logic. Instead of that, we are using the soft relays or software relays. Solid state relays with no moving parts may be used to switch on the large load of the system being controlled. In RLL programs, inputs are represented at contacts. Two types of contacts are used, namely the normally open and normally closed contacts. So how the electromagnetic relays are working, so here schematic has been shown. So where you can see the power of the relay circuit, then there is a switch and a relay coil, and there will be contact. So these are the primary components of any electromagnetic relay, where you can see that the real picture where these are the contacts. So this is the coil, and another most important thing is the spring. Okay, so this spring is playing a very important role to execute the control logic. So how it is going to execute the control logic, that is normally open and as is normally open and normally closed. Now when the current is in the coil, the armature is attached to the core. So this is the armature and this is the core. Then when the current in the coil, then what will happen, this armature will be attracted by the core. As it is attracted, then what will happen, the armature is attached to the core. The movement of the armature against the spring force, means this attractive force should overcome the spring force. Then what will happen, the movement of the armature against the spring closes the contact. So when it will go upwards, then these are the contacts are going to be closed. And from here we can understand very easily what is the concept of normally open and normally closed relay or logic. So when there is current in the relay coil, then normally open contact closes. Okay, so whenever so it is normally open, whenever there is a current, then the relay coil, the normally open contact closes. When there is no current in the relay coil, the normally open contacts remain open. When there is current in the relay coil, then normally closed contacts opens. When there is no current in the relay, then the normally closed contact closed. So the ladder logic, since PLC evolved out of relay control panels, the PLCs adopted legacy concepts which were applicable to such panels to facilitate maintenance and modification of the physically wired control logic. The control panel was systematically organized so that each control formed a rung much like a rung on a ladder. Okay, so this way the PLC logic is developed. The development of PLC retained the ladder logic concept, where control circuits are defined like rungs on a ladder, where each rungs begins with one or more inputs and each rung usually ends with only one output. A typical PLC ladder structure is shown in the figure. So here you see, so each rung is representing the logical expression or logic function realized with relay, and you can see the two power rails are there, and each rung is representing the relay logic, and there must be multiple rung, but one thing you have to remember that each rung must end with a single output coil. Okay, so that is the very important when you are developing any logic to execute certain operation. Okay, now these are the certain symbols are used. So for the control relay, so this is the NO, NC, normally open, normally closed. So this is the control relay. Then timer relay, that is TR, and then NO, NC contacts are will be contacts will be represented by this. And certain output symbols are motor, solenoid valve, then pilot lamp or lights will be represented by these figures. And some switches are also standard symbols are there, that is PB1, push button 1, push button 2, which is momentarily action push button, that is normally open and normally closed. That is limit switches, then pressure limit, temperature limit, and level limits. Now a very important thing is that how the PLC is going to execute the programming which is written inside the memory of a PLC. Now you see, this is the actual hardware electrical ladder circuit has to be executed. There are two push button switches, PB1, PB2, and there one LS1, that is the limit switch, and it is going to control a pilot lamp. But this PB1 and PB2 are in parallel, which is ANDed with LS1. Now if we want to write the program as a ladder diagram, we have to write this logic inside the memory with the help of the contacts and coils available inside the memory. So now we can write the programming inside the memory, but how we will identify the switches? So for that, actually you have to give a naming based on their connection. Now you see the PB1, PB2 and LS1, they are connected with the terminal of the PLC inputs 30, 31, 32. So we can give the name of these inputs which is represented by the contacts, that is 30, 31 and 32, and the output which is connected at the output and 40, then we can identify the output as a 40. So with that we can write the programming inside the memory. Then as the inputs are going to change its status, okay, maybe PB1 is closed, PB2 is not closed, LS1 is closed. So depending on the status of the switches, okay, so these are the switches which is present here, okay. So depending on the status of the switches, the output is going to be going to be on or off based on the logic what it is written inside the memory. Okay, so in suppose that switch 1 is closed, suppose switch 1 is closed, and also the switch 2 means 30 is closed, 31 is also closed, and also this is also closed. Then what will happen if these three switches are closed simultaneously? Then the pilot lamp 1 is going to glow. So in this way, now we can see that the status of the output is going to be changed depending on the input condition. But in details we have to know how the program cycle is executed. So that's why in the next topic we are going to understand program execution. A very commonly used method of programming PLCs is based on use of ladder diagram. The ladder diagram consists of two vertical lines representing the power rails. Circuits are connected as horizontal lines, which is the rungs of the ladder between these two verticals. In drawing a ladder diagram, certain conventions are adopted. Once again, I am repeating that one. The vertical lines of the diagram represents the power rails between which the circuits are connected, means each logic is connected. The power flow is taken from the left hand vertical across a rung. Each rung on the ladder defines one operation in the control process. A ladder diagram is read from left to right and from top to bottom. Sorry, maybe I will come this one again when I will show you a particular diagram. So let us see how the program execution is done, and then only the scan cycle of a PLC will be clear. There are different ways and means of executing a user program. Normally, a cycle execution program is preferred, and this cycle operators are given due properties. Program processing in a PLC happens cyclically with the following execution. What is the step 1? Now, after the PLC is initialized, the processor reads the individual inputs. The status of the input is stored in the process image table, that is PII. The processor processes the program stored in the program memory. This consists of a list of logic functions and instructions which are successively processed so that the required input information will already be accessed before the read in PII, and the matching results are written in the process image output table, PIO. Also, other storage areas for counters, timers, memory bits will be accessed during the program processing by the processor if necessary. In the third step, after the processing of the user program, the status from the PIO will transfer to the outputs and then be switched on or off. Afterwards, it begins the execution of the next cycle from the step 1. So, this is the scanning cycle or scan time of a PLC. The time required by the processor to complete one cycle is known as scan time. After all rungs have been tested, the PLC then starts over again with the first rung. Of course, the scan time of a particular processor is a function of speed of the processor module, length of the ladder diagram, type of the instruction executed, actual ladder true-false conditions, and the PLC computes the scan time each time the end instruction is executed. So this is the typical scan cycle of a PLC: initialize, read all inputs, then program, then updates all output. Once it is complete and it is going to encounter the end, then it is again going to do the same or going to repeat the same cycle. And which is pictorially represented. You see the input modules, the input data is stored as an input image table file. Then during the program execution, the status of the inputs are called, and accordingly the status in the input inside the programs are changed, and the output is determined, and that output again going to be written at the output image table. And then from this output image table, the status of the output is going to the output modules, transfer to the output modules. Here also same thing has been pictorially, it has been shown, that is in first the input scan, then the program scan, then the output scan. And here one thing I want to mention, that the scan time of a PLC is in milliseconds, so it is extremely fast, and that's why it is very much popular for the shutdown operation in a plant or emergency shutdown operation in a plant. So here you see how the program execution is done. So first rung A will be read, then rung B will be read, then rung C will be read, and then end of the ladder will be encountered, and again it will go back to the first rung. So in this way the execution will be done. Scan process applied to a single rung program. So again it has been shown by pictorially such that your understanding will be clear. So this is the input device which is actually in the field. The status of the input is connected with the input module. The input module which connected with the processor of the PLC. The status of the input is written in the input image table, and here the input is identified its address. In the next lecture we are going to know that how what are the addressing schemes are available for the input and output addressing. Then the depending on the logic, the output is going to be energized, and you see the output also having a address. The status of the output will be written in the output image table. From there it is going to be transferred to the output module with which the output is connected, and ultimately based on the logic, whatever the status of the output, it will be reflected at the output device. And same thing can be seen for the multiple rung program. Here what will happen, the image table having multiple status of the inputs, and then step 2 solve the ladder program, and step 3 when it is going to encounter the end of the ladder, it is going to be written in the output image table, which is going to transfer the output module. So now, as a summary, we can say that each rung must start with an input or inputs and must end with at least one output. That is the very important thing you have to remember. The term input is used for a control action such as closing the contacts of a switch. The term output is used for a device connected to the output of a PLC such as a motor. As the program is scanned, the outputs are not updated instantaneously, but the results stored in memory and all the outputs are updated simultaneously at the end of the program scan. Electrical devices are shown in their normal condition. Thus, a switch that is normally open until some object closes it is shown as open on the ladder diagram. A switch that is normally closed is shown closed. A particular device can appear in more than one rung of a ladder. For example, we might have relay that switches one or more devices. The same letters and or numbers are used to label the device in each situation. The input and outputs are all identified by their addresses. The notation used depends on the PLC manufacturer. This is the address of the input or output in the memory of the PLC. So in the next class, we are going to understand that how the addressing schemes are there to identify the input and output of the PLC, along with the what are the basic registers are available in the PLC, which will be helpful to us to develop the PLC programming. Thank you.